Hi Flat Earthers, this is Zach. Well, NSA can track you by using 3-cell towers. Your location can be tracked fairly accurately by someone who is measuring your triangulated points among the 3-cell towers. Now my point is, why don't we use the same techniques to locate and track the sun? Of course we don't have cell towers, but we got something similar. Sun rays, in other words, elevation angles. We can do this either on a ball or on a flat ground. But in this video, I'm just going to show you how to track the sun on the flat ground only. So if you are a globe believer, this video is not for you, so don't waste your time watching it. I'm telling you. Flat Earthers, there is a way to make a real flat earth model based on reality. If we do this perfectly, no one will ever be able to debunk us. So in this video, I'm going to show you a few things. How to locate the sun, how to measure the distance to the sun, how to draw the path of the sun, and how to measure the speed of the sun. Tracing the sun can help us know a lot of things, and the most important thing that we should start with is make an accurate flat earth map. No, it's not impossible. We just need to help each other. But we will talk about this in the future. And don't worry, I'm not going to reject the flat earth just because I can't draw the flat earth map. It's like a puzzle to me, and I am a big fan of puzzles. Now to cut to the chase, let me show you a little experiments I made at home to make sure that my idea really works. But before I show you the real experiments, let me explain it to you. So what I did was measure the distance between the lamp and the ground using the elevation angles of 3 points and also the distances between them. I should have used the compass to know the direction of the lamp, but I didn't, because it's going to be really complicated and not precise enough to measure long distances like the distance to the sun from 3 far countries. Yet, we're going to need people with a compass in every place on this earth to draw an accurate flat earth map. And I'm going to talk about this in another video. Now let's go back to the experiment. So if we are going to draw this in AutoCAD, and all we have is distances between 3 points and elevation angles, then we need to invent something to replace the compass. And I got a pretty good idea. So these are the 3 points, A, B, and C. I'm gonna need to place 3 objects on each point to get the shadows and to measure the elevation angles. And I'm gonna measure the distances between these 3 points. Now this line should go to the lamp, but in AutoCAD we're not going to know the direction of the shadows. So what I'm going to do is draw a circle with the radius of this shadow, and I'm going to do the same thing with the other objects. Now any line I draw from the circles to the top of the objects can take us to the lamp, but to locate it we're going to have to draw like millions of lines from these circles, and 3 of these lines will intersect in one point, and that point is going to be the lamp. But to avoid drawing millions of lines, I'm going to draw a shape like this, but in AutoCAD it will look like this, and you will understand this better when you see it in AutoCAD. Just stay with me. Okay, now let's do the experiment. Here we go. Let's switch on the light so you can see it better. Well, as you can see, I got 3 lighters and 3 white points, C, A, and B. I put these points here so I can measure the distances correctly, and I have already done that, so I'm just showing you how I did it so you can understand what I'm going to do later. Well, I'm going to use the distances between the lighters and the shadows to get the angles of elevation. I'm actually going to take all the measurements and represent them all in AutoCAD except the altitude of the lamp, which I'm going to try to locate by the elevation angles only. So let's imagine the lamp as the sun and the lighters as cell towers, and the light that comes from the lamp as a mobile signal, for example. And all we have is distances between the towers and the mobile signal, which is the lights in this case. Here are the measurements that I used to locate the lamp that is at 35.50. Now the question is, how are we going to locate the lamp using the distances between the lighters and the elevation angles only? Let me show you this in AutoCAD, and if this works, then we're gonna have to do the same thing with the sun. Okay, now what you see here is exactly what I had on the table. same measurements. Look at the distances and compare them to the distances I showed you on the paper. I'm gonna do this as slowly as possible so you guys can follow me, okay? So please pay attention here because I will be doing this faster when we start to measure the distance to the sun on the world map. So these are the lighters. The lamp must be somewhere here, but we still don't know for sure. I'm gonna delete these lines because I'm not gonna need them anymore. And now I'm gonna draw the shape I told you about. The shape is gonna keep the same angle of 360 degrees, but it's not necessary to close the shape because we already know that the lamp is in the middle. Remember, we are triangulating the lamp. Now let's rotate it towards the middle. There you go. Now I'm gonna stretch it out a little bit just in case. Now let's do the same thing with points B. There you go. Now we are going to rotate it. Well, as you can see, it intersects in an arc, and the lamp can be anywhere on that arc. So to locate the lamp, we're gonna have to draw the third shape. Okay, we're done. Now let's change the color so you can see it better. You see, they intersect in one point, so that point is the lamp. Now I am going to draw a little sphere there. Let's say it is the lamp. There you go. That's our lamp. Now, all we gotta do is measure the distance from the lamp to the ground and compare it with the one I measured live. So the exact distance is 35.44 and the expected distance was 35.50 approximately. And this little difference wouldn't have existed if I'd measured the distance from the table to the center of the lamp and not to the shade holder, because the lines go to the center and not to the shade holder. Now, before I show you anything on the map, let me show you first the exact distance to the sun using the exact distances from Google Maps. So I'm gonna choose 3 cities: Madrid, Cape Town, and Ushuaia. So let's start with Madrid, Cape Town. This is the distance between them. And now I'm gonna draw the exact distance in AutoCAD. Now let's see the distance between Madrid and Ushuaia. Here it is. Now I'm gonna draw a circle with the radius of that distance. Now let's see Cape Town and Ushuaia. Here it is. And now I'm gonna put another circle here with the radius of that distance too. There you go. Now you can say we got the 3 cities in AutoCAD. Now let me write the names quickly: Madrid, Ushuaia, and Cape Town. Now I'm gonna draw these vertical lines because they are necessary to draw that shape we talked about before. Alright, this is how it looks like. Now I'm gonna add 3 circles just because I want to, okay? And now I want you to check this out. Do you see that? That is the altitude of the sun, or the solar elevation angle. And that is exactly what we're gonna draw in AutoCAD to locate the sun. And by the way, I'm going to do this on the cylindrical projection map, so just keep watching, okay? So this is Cape Town, and I'm gonna change the time to 2 p.m. Madrid time, 3 p.m. in Cape Town. So the angle of elevation is 57.86 degrees. Now I'm gonna go ahead and draw this angle in AutoCAD, 57.86 degrees. Okay, perfect. Now let's see Ashwaya 31.89 degrees. Let's do it quickly. That's perfect. Now let's see Madrid. 33.06 degrees. Okay, cool. Now it's time to draw that shape that I like very much. I'm doing it quickly, but you can play in slow motion so you can see it better. As I told you before, this shape is just to replace the compass and the azimuth, and to me this is more precise and easier to do. Okay, I'm changing the colors now. Now that is the location of the sun. I'm gonna draw a little ball there, and I'm gonna give it like 34 miles in radius just to see how small it's gonna look like in comparison with the Earth. And now let's measure the distance from the sun to the ground. 2,584 miles. So if the distances between Madrid, Ushuaia, and Cape Town are correct, then the distance to the sun is correct too. So this is how the sun is going to look like on the flat Earth. Now let's open the flat Earth map in AutoCAD and see if you can work on it or choose a cylindrical projection. Here it is. I tried to make the distance between Madrid and Cape Town as correct as possible. As you can see, it's almost the same. But there is a problem here. If we measure the distance from Cape Town to Ushuaia, the distance will be completely exaggerated. So we can't work on it. Let's see the distance from Madrid, Ushuaia. I'm pretty sure we will get an exaggerated distance too. Here it is. So, no, we can't work on this map. But we can work on this one for the moment until we get an accurate flat Earth map. So I put a vertical line on the center of each city as usual. Well, I think you already noticed that the lines don't look exactly on the right places. But don't worry about that. That is just a graphic problem. I promise. Everything is on the right place and everything gets organized once I zoom in. You see that? It's right in the center of Cape Town. The same thing in Ushuaia and Madrid. Let's take a look at Madrid too. Now let me show you that the distance from Madrid to Ushuaia is not correct, and we already know that, okay? We know that this map is not accurate. The only correct distance is from Madrid to Cape Town. Now let's start measuring the sun. So this is the altitude of the sun in Madrid, 33.06. 33.06. So here it is. Let me confirm it. Okay, that's perfect. Now let's move to Cape Town. 57.86 degrees. I'm actually drawing the same angles over and over again. Now let's write it here, 57.86 degrees. Let's make sure it's correct. Okay, perfect. Now let's move to Ushuaia again. And let's do it quickly. Okay, 31.89 degrees. Make sure it's correct. Okay. Now let's take a look at the drawing. I think you guys have an idea where the sun is gonna be. This time I'm gonna show you more stuff. Just stay with me. Now it's time to locate the sun with that beautiful shape. Let's do this fast because I don't want you to sleep. Okay, now let's change the colors. That's where the sun should be. Now I'm gonna delete these shapes to see how small the sun would look like. And by the way, the radius of the sun here is 34 miles, okay? I know it's bigger than what the flat earthers say. I just wanted it to be more visible, that's why. So that is the location of the sun. The sun is about the point that I'm gonna show you right now. Now I'm gonna show you the distance from that point to the sun. 3,052 miles. Let me show you the distance from each city to the sun just in case you are curious to know it. So this is how we triangulate the sun and the moon and any lights in the sky. Now I'm going to show you how to draw the path of the sun and how to measure its speed. What we're going to do now is change the time from 2 p.m. to 3 p.m. Spain time, but we're not going to change the date. We just want to see where the sun is going to be after 1 hour. So the altitude in Ushuaia is 39.65 degrees. So I'm going to write it here, 39.65. Now I'm going to move to Cape Town and the altitude is 46.11 degrees. Let's draw the angle here, 46.11 degrees. Now let's see Madrid and the altitude is 29.72 degrees. Okay, now I'm going to write it here. Alright, that's correct. Now I'm going to get rid of the other lines. They're not necessary anymore. So let's draw the shapes. Y'all know the steps now, right? This is the first shape, and this is the second shape. And here is the third one. Alright. And again, I'm going to change the colors. And now I'm going to create a ball as big as the other one, 34 miles in radius. And again, I'm just going to delete all the unnecessary lines. So this is what we got as expected. Can you see the second sun? Now I'm going to do the same thing as before to see its location on the ground. And now I'm going to draw a line from that point to the sun. As you can see, these altitudes are almost equal. And that can mean either the sun changes the altitude or the map is not accurate, or both. But I think if the map was accurate, we would get the same altitude. Now we're going to measure the speed of the sun. So the distance between the first sun and the second sun is the speed that the sun travels per hour. So the speed of the sun is 1,357 miles per hour. This is just an approximate number because the map is not accurate, okay? If we draw an accurate map, then we can measure the exact speed and the exact distances with zero mistakes. We have seen 2 p.m. and 3 p.m. Now let's see 4 p.m. So I'm going to start with Madrid. I already changed the time to 4 p.m. and the altitude is 23.61 degrees. Now let's move to Cape Town and the altitude is 33.78 degrees. Let's draw the angle. And we're going to do the same thing with Ushuaia, 46.03 degrees. Let's draw it here. And as always, we have to draw that beautiful shape. And I'm going to draw another ball here with the same radius as the other ones. And now we're going to get rid of the unnecessary lines. And now let's see its position on the earth. Now we can notice a bigger difference in the altitude and also in the speed. And that was expected because of the map. So as you can see, we can perfectly draw the path of the sun and measure the distance of every single light in the sky using this powerful and incredible software. Now let's compare the distances from Madrid to the sun at 2 p.m. and at 4 p.m. As you can see, at 4 p.m., the distance is more than 1,000 miles longer than in 2 p.m. And that means that the more the sun moves to the west, the more it moves away from Madrid until it finally disappears. And this should tell you something, huh? So this is how I measure the distance to the sun, and this is how I'm gonna make an accurate flat earth map. The way we triangulated the sun from 3 cities on the earth is the same way we are going to triangulate a city from 3 lights in the sky, or from 3 positions of the sun. And in my next videos, I'm gonna explain this better because I'm gonna need a lot of help from everyone, especially graphic designers, architects, professional video makers, and even painters. So anyone who can have a better idea how to draw a real flat earth map, please send me a message to this email.